Now we're going to look at how concentration affects cell potential. As I mentioned earlier in the other videos, a standard cell, 25 degrees Celsius, 1 atmosphere for any gases, 1 molar for any solutions that you set up in your cell. And really what starts to happen, if you can kind of think of how those cells run, as the cell runs, the concentration of one ion is going to increase from 1 molar and the concentration of the other ion is going to decrease from 1 molar. So really it's when we initially set those up that we see what these exact cell potentials are for the cell in general. And then it starts to decrease over time, just like any battery would start to wear out over time as more and more of your reactants are transferred to products. So how cell potential is affected by concentration is through the Nernst equation. I know I just pulled a lot of things up right there, but basically I want to get down here to this last equation. Okay, that is the Nernst equation. So remember this up here in the upper left, this was how delta G, the standard delta G, changed with either pressure or concentration. And after we derive this whole equation, again, the derivation of the equation is not that important. The actual Nernst equation isn't even on the AP exam, but it is, something important for this chapter, so I did want to include it. So really what we're looking at here is how does the standard cell potential change when we have changing concentration? Okay, so that Q, remember, that's going to be your reaction quotient, products over reactants raised to the power of their coefficient. So if we're not at 1 molar and we have different concentrations, what's the new cell potential going to be? So this next example problem shows that. It says, will the following reaction occur spontaneously at 25 degrees Celsius if the iron 2 concentration is 0.6 molar and the cadmium ion concentration is 0.01 molar, according to this equation. So again, if the equation's written, that's how we have to take it. The iron 2 is going to iron and the cadmium is going to cadmium plus 2. Okay, so the oxidation is the cadmium to cadmium 2. With 2 electrons, the reduction is your iron going from iron 2 to iron. So then when we find the cell potential, again, I'm sorry, N is equal to 2 because we have 2 electrons being transferred. We have negative 0.44 volts plus a positive 0.40 volts because we had to flip that one to the oxidation. And we get an overall cell potential of negative 0.04 volts. So non-spontaneous in the direction written, a very small negative voltage would be produced. Now, let's see, this would be if we had 1 molar of each of our solutions, but we don't. We have 0.60 molar of the iron 2 and 0.01 molar of the cadmium. So if we use the Nernst equation, here it is. What is the new cell potential? So this will be your new cell potential from your standard under these conditions. So let's see what that would look like. Negative 0.04 volts, that's our standard. 0.0591 over 2. Again, we're at 25 degrees Celsius, so we can combine R, we can combine T, we can combine F. And then we have the log of 0.01. Okay, that's this concentration of the cadmium over 0.6. That's the concentration of the iron 2. We don't have to square anything. Everything has a coefficient of 1. So when we do the math, we get that we have a positive 0.013 volt value for our cell potential. So it actually made having these different concentrations actually made a non-spontaneous reaction spontaneous because of the concentration. Okay, so the cell potential is now greater than 0. Okay, so it's spontaneous.